Merci Abdoulaye et bonjour à toutes et tous. So I will now switch to English to introduce our next speaker, Jan Reineke. We will talk about probably timing predictable microarchitectures. So Jan is a professor of computer science at Saarland University in Saarbrücken, Germany, where he leads the real-time and embedded systems labs. And he works at the hardware-software interface with application both in real-time systems and security. In the field of real-time system, he recently contributed to the first Provably timing predictable pipeline processor, and also the first exact analysis of LRU caches. And for this contribution, he got award at the flagship conference on real-time system, so the real-time system symposium. In the domain of security, he developed recently automatic techniques to detect vulnerabilities introduced by speculative execution techniques, as well as automatic techniques to quantify the information leakage through side channel attacks. And last but not least, he has been recently awarded an advanced grant from the European Research Council for a program about abstractions for safe and secure hardware systems. So Jan, please.
Thank you very much. Thank you very much for the invitation. And so as Sébastien has already introduced, so my topic is going to be provably timing predictable microarchitectures. And this is joint work mostly with Sebastian Hahn, who has been the lead PhD student behind this, and also a little bit with Johannes Kahn, who is still an undergrad, but a very smart guy. So look out for him in the future. What is this about? Just a little bit about the context, right? So the context of this work are hard real-time systems. So those are systems in which software interacts via some hardware with the physical environment, and this interaction with the physical environment imposes strict timing constraints. All right, so the classical example, maybe not the most challenging example, is an airbag controller, where clearly there is a strict timing constraint in which the software needs to detect via sensors that an accident is occurring, and it needs to decide to fire the airbag. And if this doesn't happen in time, then obviously the airbag isn't very useful, right? So there, the timing constraints are relatively loose, but there are other problems, for example, in airplanes and also in trains, where it's much more challenging to meet the requirements. Right? Of course, such embedded software needs to deliver the correct control signals, but the focus of my work here is on fixing or determining that the time bounds are also met. Right? So the problem that we're facing abstractly is that we are given a piece of software that is going to be executed on a piece of hardware, and we need to check whether that hardware will be able to execute the software within the time bounds that are imposed by the environment. Okay, so what does the execution time of software on hardware depend upon? Clearly, if you write a piece of code, the input of that program, depending on the program that you write, may determine the path that you take through the program, and that is going to influence your execution time. And this is something that is really completely independent of the hardware, right? That's not something that you can do anything about at the hardware level. But actually, there are many more challenges that are particularly due to the microarchitecture on which you're executing your code. And one aspect here is that modern systems have a number of concepts that introduce variability into the execution time of individual instructions based on the history of execution. Okay, so for example, caches, pipelining, speculation mechanisms that you find in all modern processors, or at least some of them you find in modern processors. So just to give you an example, if you have such a small piece of code, say your program just consists of an addition of 2 variables, then that may translate into 3 assembly commands. And if you run those on a PowerPC, which is a rather dated processor that is actually flying in Airbuses today, then you can see that the execution time of these 3 instructions varies dramatically based on the state of the cache at the start of the execution of this piece of code, right? So if both of these loads result in cache misses, then you will see an execution time of about 300 cycles. And if both of them hit, then you will have just a couple of cycles to execute these things. Okay, so that's a challenge. And an increasing challenge due to the introduction of multi-core processors and many-core processors is that the execution time also depends on interference from the environment. Okay, so where the environment is defined to be sort of everything on the microarchitecture that is not directly responsible for executing the code that you're running. Right? For example, you might be analyzing a task that is running on one of the cores of a multi-core, and now this may interfere with code executing on other cores, which is then using shared resources such as shared buses or shared caches or shared memory. And just to give you an example of the impact of such interference, Radojkovic et al. About 10 years ago already determined that you can see up to a 14x slowdown due to interference on shared L2 caches and memory controllers, right? Which is completely negating any benefits that you may have of using a quad-core processor if now things are running 14 times slower due to interference. Okay. So my work, or the work that I'm going to present today, mainly deals with these last two aspects, right? So I cannot do anything about the software, but I can do something about the influence of the state of the hardware platform and also the influence of interference on the execution time of some code. And I want to start this discussion by kind of mentioning two schools of thought, right? So if you look into the literature about what a predictable microarchitecture should do, right? So how should we design the hardware such that these problems go away? Then I think you see basically two different stories. And these can be explained to some extent using this figure. So what you see here is on the x-axis execution time, and on the y-axis, sort of the frequency of observing different times, right? So if you have a given program, depending on the inputs, depending on the interference, you will see, potentially you will see differing execution times, and that gives you some sort of distribution where all of these execution times lie between the best case and the worst case execution time. And our goal typically is to compute the WCT or to upper bound it, right? And so the first sort of school of thought with respect to predictability is that we should aim for microarchitectures that minimize the ratio between the worst case and the best case, right? So intuitively, if your worst case execution time is equal to your best case execution time, then predicting its timing behavior is really easy, right? You run it once, you observe some execution time, and that's the execution time you will see in all executions. Okay, so essentially, if you minimize this completely, if this ratio is 1, then you get deterministic timing. And I totally agree with the observation that that is a nice property to have. But I think that this is too restrictive a goal, which basically imposes a lot of inefficiency into your design. Okay, so what I will argue for is a kind of different notion of predictability, and that is that we should not worry about the ratio between the worst case and the best case execution time, but we should worry about our ability to efficiently approximate and precisely approximate this worst case execution time. Okay, so basically, if I want to prove that the timing bound is met, then all I care about is the worst case execution time, and I don't really care whether, sometimes it's even executed much faster. Okay, and so now the question is, what are the properties that our microarchitecture should have that enable us to perform such efficient predictions? Okay. So if you now look into the literature, and you look even almost 25 years back, you find certain challenges that prohibit efficient prediction of the worst case execution time. And the major challenge there are so-called timing anomalies. Okay, so what are these timing anomalies? So these timing anomalies arise from the fact that we have this apparent non-determinism, right? So if I look back here, we have this variability in the execution time, and this stems from, if you abstract from certain things, from non-determinism in the behavior of the system. So we can model the behavior of the system typically as some sort of transition system where you may have non-determinism because you don't know the state of certain components, or you don't know whether interference will occur, you know, in a multi-core system, and that gives you this large state space that you would have to explore if you don't have certain, if there's no special structure to your system. And what you would hope for is that, sometimes this non-determinism, you can kind of attribute it to certain events happening in the hardware. For example, if you have a cache, you might have the case that your memory access results in a cache hit, and you may have the case that the memory access results in a cache hit. And so intuitively, the cache hit will take a smaller amount of time than the cache miss. So you would hope that, and if you are interested only in the worst case behavior, that it would be sufficient to just consider the local worst case, the cache miss. Right? Now, unfortunately, what Lundquist and Stenström observed in '99 was that there are cases in modern hardware where actually the successor states of this cache hit case do result in the global worst case execution time. Okay, so the consequence of this is that you cannot just disregard these local best cases and just follow the local worst case in order to arrive at an upper bound on the execution. So it would be really nice if we could get rid of these timing anomalies. Right? Okay. Another example, even quite a bit older, from the 60s, Ronald Graham, who was a kind of preeminent mathematician, considered a multiprocessor scheduling, and he realized there that if you do non-preemptive scheduling, then you have scenarios such as the one depicted here. So we have these three tasks, A, B, C, D, E, with some dependencies, and we have two resources on which these are executed. And if you change certain parameters in a way that makes things better, right? So for example, here, C is ready to execute at this point, and A takes a long time in the first example, right? And if you now do non-preemptive scheduling, you arrive at this schedule. Whereas if A finishes earlier and you apply a certain deterministic scheduling policy, then you get these scheduling anomalies where even though things improved locally, your global execution time increases, right? And if you think about modern processors, what they do at the very fine granular level is they do scheduling of these small operations, a execution of micro-ops or execution of instructions, and they have a bunch of resources that are shared, and you will observe such scenarios there, and that results in these timing anomalies. Okay, so having the absence of timing anomalies is sort of one goal for timing predictable microarchitecture. A second goal that is very related, as we will see in a minute, is to achieve so-called timing compositionality. And let me explain that to you at the hand of an example. Right, so let's say you are faced with the timing analysis problem for a multi-core processor, and this task that you're analyzing is supposed to run on core 1, right? But it will have to access the shared memory via a shared bus once in a while, right? Now, what you would like to do is you would like to sort of divide and conquer and separate your problem into sub-problems and then compose the results of these sub-problems to arrive at an execution time bound, right? So intuitively, what you would like to do is you would like to analyze, how long is it going to execute on the core? How often is it going to use the shared bus? And how often is it going to use the shared memory? And then determine that also for other tasks, compose their effects, and determine an execution time bound for the program as a whole. And in fact, this ability to perform timing analysis in such a way is actually implicitly and sometimes also explicitly assumed in basically all approaches that you find, for timing analysis of multi-cores and cache-related preemption delays in the literature. Okay, so intuitively, the benefit of this is that, instead of analyzing this very complex large system, we can analyze each component separately. And instead of having sort of the product of the state spaces, we just have to consider the sum of the state spaces in the analysis. Okay, so timing compositionality is clearly is another very nice goal. Okay, so can we get timing compositionality, and can we have the absence of timing anomalies? So let's consider a sort of super simple textbook in order pipeline, as you may teach it in your undergraduate courses, right? So you would have these 5 stages: fetch, decode, execute, memory, and write back. And to make it a little more interesting, we add caches here, right? Because if we don't have caches, performance is going to be terrible. And these caches are now connected to memory. Now, if you can study such a very simple design, right? No speculation, no out of order execution, nothing. You still find that such processors have timing anomalies. And unfortunately, for lack of time, I can't go into the details of why this happens, but I can give you an intuition. And the intuition is that there is this shared resource here, which is the memory, that is accessed both from the instruction cache and for the data cache. Memory accesses are happening in a non-preemptive way, and the fetch and the memory stage compete for these accesses. And then you can construct scenarios where, for example, a cache hit in the instruction fetch case leads to reordering of things, and then you get your anomalies. And similarly for cache hits or misses for the memory. Okay. Now, let's say we want to analyze this processor in a compositional way. Right? Let's say we want to separate the execution on the pipeline from the cache behavior. If you want to do that, then you need to somehow determine what's the cost of an additional cache miss, so that you can compose the execution times from the pipeline and from the cache. Intuitively, you would think, well, one cache miss, it might cost me 1 time the main memory latency, right? Like, how long does it take to fetch that data from memory? Unfortunately, if you look at it carefully, even in this very simple design, you get almost 2 times this cost, right? And the problem is that basically an ongoing instruction fetch that may have just started may block a load that is on the critical path, and vice versa. And in this way, your cost is actually twice the cost that you would hope to have. Okay, so what can we do about it? And here is sort of the key insight of our work. And that is, if you have a timing anomaly, so let's consider this timing anomaly scenario again, right? So in the timing anomaly scenario, what happens is that you have these 2 options. So you have some analysis state and you have 2 successor states, a local worst case and a local best case. And the local worst case, if you continue sort of analyzing how states progress, will eventually reach a state where the program is terminated. And this will happen before some of the successors of the local best case, right? So in particular, if you consider the successors at the same distance here from the first successors, then you have a case where the program has terminated here, but it hasn't terminated there. Now, let's introduce a notion of progress in the execution of the program, right? So let's say we have a partial order that relates 2 different states, where 2 states are ordered if, here in this case, the blue state has the same or more progress than the red state for the execution of all instructions in your program. And typically, if you have such a case of a local best case and a local worst case, this state here has more progress than that state. On the other hand, when the program has terminated down here, then the red state clearly has more progress than the blue state, because here the program is done and here there's still work to do. Right? And so the observation now is that this can only happen if my transition relation is non-monotonic. So in other words, by contraposition, if I have monotonicity in this relation, then I cannot have such scenarios. Okay, so let's sort of prove that by graphics. So let's say we have this case again, local worst case, local best case, and let's assume we have the fact that this transition relation is monotonic. Okay, meaning that if I have two states that are ordered, then their successors are also going to be ordered. Then this will hold for all successors by monotonicity, right? And so I cannot have this timing anomaly case. Okay, let me look at the time. So I guess I'm running a little bit late. So what we can also show is that that monotonicity also gives you timing compositionality in a simple way. So basically what you can typically show is that if you follow the local worst case and then you take a few more steps, then you can show that the state that you reach will have more progress than the one that you got after the local best case. And that will allow you to reason that this penalty, this time that it takes to overtake the local best case, is an upper bound on the cost of any such event. Okay, so monotonicity is great, but how can we achieve it? Right, and as I mentioned before, it's really, in this case, due to this shared resource, which is the memory, which may be accessed out of order. And pipelining itself isn't really the problem. And so this led us to define a strictly in order pipeline. And this is a pipeline, or this is any pipeline in which each resource is accessed in program order. And this now would include also this main memory, right? And there are different ways of enforcing that. A simple way of enforcing that is to block instruction fetches until potential data accesses have occurred. And if you do that, then you do indeed get monotonicity. Let me skip over this. So we can prove basically that for every successor here of a state that has more progress, there exists a successor there that will have less progress there. And the corollary of achieving monotonicity in the strictly in order pipeline is that we provably have no timing anomalies and that we can do compositional analysis with what I would call natural penalties. Okay, so you may wonder, what's the cost of imposing monotonicity, right? And so here are just the key results. So in terms of performance, we have a loss of about 6% in performance compared with a regular in-order pipeline. So we get almost all of the benefits of pipelining. So if you remove pipelining completely, you lose about a factor of 2 or 3. Here we lose 6%, but so we have non-determinism in the execution time, but our analysis is very efficient in determining the worst case. So in particular, our single core analysis is about 4 times faster, and a multi-core analysis is about 32 times faster than for a standard in-order processor. Okay, I think I will skip over the approach that we have for automating such predictability proofs. So what I've shown you before, we did kind of pen and paper proofs, right, on a kind of also pen and paper model of what the processor is doing. And as a next step, what we wanted to try is, to see how much we can automate this process in order to gain more confidence in that the actual implementation of our design has the desired monotonicity property, and it's not just something that we dreamt up on paper. Okay, and so what we did there was to basically formalize the processor, formalize the property, and reduce the problem to queries to an SMT solver. And there are certain problems to this. So one is that you get infinite state spaces. And another is that when you do this naively, you start defining this formula, which should be unsatisfiable if monotonicity holds. And you try this out, and it turns out your formula is satisfiable. And the reason for that is that you need to capture invariance of the system. And when you do that, then the proof actually succeeds, and you have a more automatic proof of the actual design rather than just this simple pen and paper proof. Okay, if you're interested, there are more details here in this journal paper. Okay, let me skip over the efficiency and come to the conclusion. So the key insight of this work has been that there's a very strong connection between monotonicity on the one hand and different notions of timing predictability. So absence of timing anomalies and also the ability to do timing compositional analysis. Both are very direct consequences of achieving monotonicity. And for in-order pipelines, this concept of strictly in order actually achieves monotonicity. Okay, so that concludes this brief introduction. I'm happy to take any questions.
Thank you very much, Jan. So we have two questions on the Q&A board, which are closely related, concerning the extension of your definition of monotonicity to more complex architecture, especially multi-core architectures. And how would you define the progression of a system composed of several programs running in parallel for defining monotonicity? Mm-hmm. And another aspect in the second question is the impact of monotonicity on other key performance indicators such as power consumption and energy efficiency.
Mm-hmm. Yes, so when it comes to multi-core processors, my view is that this compositional analysis approach makes more sense than an integrated analysis. So basically there you have two options. You could either sort of model the entire system as this very complex beast where you know, a state consists not only of the state of a single processor, of a single core and a program running on that core, but the state of all of these cores. I think it still makes sense to focus on one core and sort of abstract from the environment. But what you then need is you need to have some bounds on the amount of interference that you get from the environment, from the other cores. And in order to deal with that, you need this compositionality aspect. And what we show is that, I mean, this strictly in order pipeline, you could put it into a multi-core processor, and you can then show that if that, you know, if the strictly in order pipeline is implemented in each of the cores, and they interfere, for example, on a shared bus, then you can efficiently analyze the effects of interference in a compositional manner. So yeah, the short answer is sort of abstract from the environment, and by monotonicity, you can then analyze compositionally. About power consumption and energy efficiency, I cannot say so much. So I'm not an expert on energy and power. My simple intuition is that those are strongly related to execution time. So the energy overhead is going to be similar to the execution time overhead. If you look at the area consumption on the chip, the difference is very negligible. So there is a little bit of overhead there, but it's on the order of like 0.1% or something. So the main difference is likely going to be the execution time, which then kind of transitively translates into energy.
Okay, thank you very much. I see one last question, but maybe you can answer on the QA board because we are a bit running out of time. So thank you once again, Jan. And I will now give Patricia the stage.